We've been talking about equilibrium constants, and we learned how we can write equilibrium constant expressions from the chemical equation, looking at the concentrations of the products raised to a power equal to their coefficient divided by the reactants, right? Well, sometimes reactions occur in the gas phase. So here we have a reaction where all the reactants and the products are gases. So now the expression for the rate equilibrium constant is going to have the same form, except it's more common to measure pressures for gases, partial pressures, than to measure concentration, right? So we put a little subscript here. Kc is the equilibrium constant with respect to concentration. Kp is the equilibrium constant with respect to pressure, and the pressures would be measured in atmospheres. Any questions about that? So the value of Kc is not necessarily equal to the value of Kp, but there is a relationship. The partial pressure of a gas in atmospheres is not the same as its concentration in molarity, and so the equilibrium constants aren't going to be the same. And here's my note to myself to show you how these are related. Start by relating molarity to partial pressure. So we'll look at the ideal gas law, Pivnert, right? PV equals nRT. Well, if we want to isolate pressure, we're going to have P is equal to nRT over V. What are the units of N? Moles. What are the units of V? Liters. What's the unit of molarity? Moles per liter. So this is equal to N over V times RT, which is equal to the molarity times the gas constant and the temperature. That make sense? So we're going to look at this relationship. So we can say that the concentration of A then is equal to the partial pressure of A divided by RT. I didn't go all the way and show you that. Not sure why. Because I forgot, that's why. But that comes from, so N over V is equal to the pressure divided by RT. This is the molarity. So for Kc in our generic equation, we're going to have A to the A and C to the C and D to the D over A to the A and B to the B. Well, if the concentration of A is equal to its partial pressure divided by RT, we could substitute that in really for all of them, right? So we're going to get the partial pressure of C divided by RT raised to the C power. Partial pressure of D over RT raised to the D power divided by partial pressure of A over RT to the A power and the partial pressure of B over RT raised to the B power. That's a mess, right? Well, what does Kp equal? Kp is equal to the partial pressure of C to the C power times the concentration of the partial pressure of D to the D power over the concentration of A, the partial pressure of A, you get the idea. Yes? So what we can do is we can factor out all of these RTs from this equation. So we'll get PC to the C, PD to the D, over PA to the A, PB to the B. And then this is 1 over RT raised to the C power. So if we want to keep it in the numerator, we could say that's RT to the negative C times RT to the negative D over RT to the negative A and RT to the negative B. That was really squishy over there. I'm sorry, that's not equals. That's multiplied. So I took all the RTs and I factored them out. I'm not going to make you do this derivation, but I want you to follow and believe that I'm not lying. So then we get to deal with exponents. Oh, I lost a negative here. So if we multiply two things raised to powers, what do we do with the exponents? We add them. So on the right side here, I'm going to get RT raised to the negative C minus D. And in the bottom, I'm going to have RT to the negative A minus B. Well, those negatives are just not real fun, are they? If we take this and write it upside down, we can make all of the negatives positive. So we've got RT to the A plus B over RT to the C plus D. And this part is Kp. So Kp times that is equal to Kp times this. Now we have the same thing here, RT. We're dividing and we have exponents, so then we subtract the exponents, right? So now we've got Kp times RT to the A plus B minus C minus D power. What? Do you remember doing things like this in math class? Or you like strangle these equations and then you pull them around and they turn into a pretzel or something? So that is equal to Kc. We could rearrange that. I'm going to do it in a different color up here and say that Kp would then be equal to Kc divided by this. Dividing by that would be changing the signs on this. So RT, and up here we have C plus D, minus A plus B. Clear as mud, right? Yeah.
How much water content is in the water? Is it settled or is it stirred up?
Real quick.
Yeah.
Thank you.
And I'm working on how to get these problems where there's a lot of writing, these slides with a lot of writing. I'm working out how I can save those as a PDF or something and post them for you. So, because I know scribbling it all down is hard for some people. And you don't necessarily want to go watch the video again just to see it and copy it down. Everybody done with that? Yeah.
I was wondering, where it says KP RTA plus B, is that you just inverting the RT fraction once you substitute the KP?
This part or this part?
So, from where you have all the pressures, and then the step right below it where you simplified it.
And then over here.
Yeah, so you just plugged in the KP for the PC, all that, and then you just inverted the RT minus C minus D.
Yeah.
What
So,
was the point? Like, is that
well,
just wanted to do that,
in retrospect, I probably shouldn't have, because then I ended up inverting it again. So if I just kept this one, I'd have KP to the RT C plus D minus A plus B. Wait a minute.
plus B minus C minus
Yeah.
C or something?
It's, yeah. There. Yeah. I'm just glad I'm not going to make you drive this. That's what it is. Doesn't help. Is that what somebody said?
No. I thought it was what you wrote the first time, but it's not. So never mind.
Yeah. Mm. I make so many mistakes in this class.
It's okay.
It is okay because, we're all just human. Okay, so let's be done with that guy.
Yes, please.
I'll have all of that.
We'll talk about
Okay.
it later.
We'll talk about that one later. No, actually, so this is a more concise way of expressing that. So what is then delta N? Delta N is the moles of gas products, which would be C and D from our generic equation, minus the moles of gas reactants. And so this is that exponent that we saw in the previous slide. And it's nice to express it this way because, so delta N, that's a difference in number of moles, and difference is usually final minus initial. So this is products minus reactants. So we don't have to try to remember that something's opposite. If the total number of moles of gas is the same before and after the reaction, then Kp is equal to Kc. Because if the sum of the product coefficients that are gases is equal to the sum of the reactant coefficients that are gases, then that'll end up being 0, right? And RT to the 0 would be 1, and then Kp would equal Kc. It's just a riot. You know, people watching this on YouTube probably wonder why there are these really long pauses. Because I can just see it slowly sinking in. There's no point in rushing it. Anybody have any questions about that? So hopefully that's good enough that you believe me that that's an okay thing. Now, I don't expect you to memorize that one. So we're looking at Kp in terms of Kc. So let's just be proactive and write that up here. Here we have, no, not that. Fine, I'll write it again. What I have trouble with this equation is remembering which side Kp goes on and which side Kc goes on. Here we have a reaction, and we're given a value of Kc, the equilibrium constant in terms of concentrations in moles per liter. And they're asking what's the value of Kp at this temperature. So before we go starting any calculations or anything, we should look at the moles of gas on each side. So how many moles of product gases? 2. How many moles of reactant gases? 2. So then we can just say, well, Kp is equal to Kc, so it's 6.2 times 10 to the 2, because delta N is equal to 0. Units of K. So we are talking about these equilibrium expressions in terms of molarities or partial pressures in atmospheres. So then if you think about what the units of the equilibrium constant would be, they're going to be different depending on the reaction, right? If you only have one product in the numerator, you would just have molarity. But if it was raised to the third power, then it'd be molarity cubed, right? So it'd be all over the place. So formally, those values of concentration or partial pressures are actually ratios of the concentration or the pressure to a reference point. The reference point is exactly 1 molar or exactly 1 atmosphere. So you don't have any units then because you're looking at, the concentration of A, that's actually equal to the concentration of A in molarity divided by 1 molar, because it's a reference. And what that does is all the units cancel out. I think that was pretty slick of them to figure out how to do that. So really this is just to say, for those of you that say, well, how can K not have units? There's units on the other side. Well, it's because it's actually this ratio where the units cancel out. So K has no units. Why did I write 3.7 molar there? Well, I think maybe I was supposed to write 3.7 molar. It's actually a ratio to 1 molar, right? And so the units cancel out, and I get 3.7. So bottom line is, as long as we use molarity and partial pressures and no other units, then we can simply ignore the units in equilibrium constant expressions. Little cheer inside. She said we could ignore the units. Under which circumstances are Kp and Kc equal for this reaction? We have if A plus B equals C plus D, if the reaction is reversible, if the equilibrium constant is small. It's A. When the number of moles of gases, which would be the sum of the coefficients for anything that's a gas, is equal on both sides, the delta N goes to 0, and Kp is equal to Kc. Any questions?